Right, what's going on here then? Let's have a listen to this.
Alright, time for the Draftscience.com video presentation. So I was working on another lever experiment, and I accidentally kind of fell upon an idea, and it sort of worked, and it might be a shortcut. It might be a way of evading having to do the actual smashing things into things with levers, and instead just use a cup.
Yeah, it might be a way of evading actually using a lever, yeah, that you claimed does what you say it does, but now you're actually trying to do that, you're realising it doesn't do what you say it does.
Both oscillators, what they're called. So here's an example of the ones you'll find online. Now they can't say for sure, okay, but I haven't been able to find any where they use uneven masses. So if somebody can find a coupled oscillator with uneven masses, like one, ideally, that would be helpful.
A coupled oscillator, what you're actually looking at is a coupled pendulum.
So the idea is one stops, okay, this one stopped, and that one's got all the energy, then this one stops, this one has all the energy. The energy is clearly moving back and forth. And
the energy is moving back and forth,
from one object to the other object. The mass and velocity move from one object to the other object. The fact is I accidentally sort of, well, it's really not an accident, I guess, because I thought of it. Why not use the lever to couple the oscillations? Because then I can have uneven masses without them knowing they're uneven masses. Okay, the lever makes them equal, and so it's sort of did in fact work to couple the twice as heavy object to the other object, and to basically create a coupled oscillator that is where all the motion is in one object and then all the motion moves to the other object. And that's basically what we want to do, is move the momentum from the heavy one and
but they are coupled. That's the thing, so they are actually all connected.
And move it to the light one, and then you move it back again, and you keep moving it back and forth, and as you keep moving it back and forth, it makes it obvious that it has to be the same amount of energy, because you're moving it back and forth, and
you're
right, go on for 15 minutes. So you're not losing very much of the energy as it cycles through, so there's no excuses about deformation or heat or air resistance or some other nonsense. It's clearly 100% of the momentum is in one object, and then 100% of the momentum is in the other object.
Right,
and because of the mass differentials, it's clear, okay, that kinetic energy isn't playing a role in.
Right, so momentum, linear momentum or angular momentum?
Anywhere. Alright, so with that stated, I guess it's worth drawing it, and then I'll link to a couple of videos that I'll leave as unlisted. So in the description, I'll put a link to the 2 raw videos, and they're just raw videos. I can improve the experiment, but I really shouldn't have to, because there should be a concession by...
Well, you were the one claiming levers did what they did.
If I can create a coupled oscillator between a twice as heavy object and a half as heavy object, that I will in fact be making it, it will not, it'll conserve momentum. If he concedes it has to conserve momentum, then he has to concede that it won't conserve kinetic energy. There'll be no evidence of kinetic.
I'm pretty sure when it comes to coupled pendulums that they do conserve energy, and they also conserve angular momentum.
Alright, so what I have done is something rather simple. So I have a suspended from the ceiling, I have my balance, my lever, and I have merely hung 7 or 8 feet on one mass.
So you've got a massive bar here, which is a huge weight, obviously, in this quite complex mechanical system. So you've opted from using a simple lever to a complex mechanical system that basically exchanges energy. Right, okay.
This is the 2 mass side. 2 mass and a 1 mass. Okay. Twice the distance. Alright, and basically how it works is, which is neat, you can actually get the motion towards each other. Now I have to do something to force them not to turn and to twist and to spin, so I can work that out. But so currently you just give this a motion, okay, force in.
Right, so you
give... What will happen is these 2 things will...
You give that one a motion. So you don't give it... You didn't say momentum, you gave it a motion. Right, okay.
Oscillate towards each other, and at one point this one will stop and all the energy will be over here, and then this one will stop and all the energy will be over here.
Yeah, that's what coupled oscillators, coupled pendulums do. That's what you call it, but yeah, they are coupled pendulums.
And conserving the momentum, and I would argue proving the point. Okay. Now, I didn't bother doing frame rates and all that crap because theoretically I shouldn't have to, because everybody should concede I can't change the amount of momentum. If it jumps back, if it keeps doing this over and over again, 10 times, 50 times, you'd have to concede that obviously it's all the momentum is going from one side to the other side.
Yeah.
So it really is your job to say,
Right. Well, the reason they just do it over and over and over is because you first put in potential energy due to gravity that converts to kinetic energy, and then back to potential energy, and back to kinetic energy, and so on and so on and so on.
We'll see.
Until it winds down.
We'll see how reasonable people are. Because this is a real concept. Everybody knows coupled oscillators, physicists will concede momentum is conserved. So
yep, angular momentum is conserved in coupled pendulums.
This one has to be not conserving kinetic energy.
And they also conserve
more kinetic energy here than you have over here. And that's nonsense. Everybody should know that can't be. I shouldn't have to explain why that would be ridiculous.
To you.
So let's find the two videos, and we'll do the forward-back one, I think, first. I just have to find that one. It should be this video, I guess. I'm pretty sure. There we go.
Okay.
All right, let's see how badly that looks. And so I should get rid of the sound, because it really isn't any. And
so,
I like the mirror.
Right, you've got the two weights hanging there, a half mass and a 1 mass, or a 2 mass and a 1 mass, however you want to say it. Are the length of those pendulums the same? Because they don't look to be. The one with is it the small mass at the furthest away? That looks to be quite a bit lower. With pendulums, the period's dictated by the length, not the weight attached to the end of the bob, but the actual length. And also in this, because you're angling it from string, you're angling a mass from string, so it's not like a compound pendulum like where you're using a rod. So the centre of mass is different. If you had a solid rod all the way down, the centre of mass is in the centre of the rod. But obviously, when you've got a mass hanging from a piece of string, the most of the mass is at the bottom, so it changes the way it behaves.
Screws it up a little, but this idea is okay. So I gave the energy to the big one, and now it's transferring.
Right,
you
gave the energy to the big one. You just got to think, when you're saying there's no kinetic energy involved in this, there's not a hint of it. You gave that large mass motion, but how did you do that? Did you put momentum into the system to get motion going, or did you pull that weight back in gravity to a height? So mgh, basically, you got a mass, you pulled it to a height, you've got the gravity, and it has potential energy due to gravity, and then you let it go, and that potential energy converts into kinetic energy, and back and forth and back and forth. So these couple pendulums are actually a very good way of showing how energy is conserved and how energy, moves from one thing to another.
And it's getting faster, its arc is getting bigger and bigger, and this one's slowing down and slowing down, and it'll eventually almost, right about there, comes to a stop. And now all the energy is in the small one, and now it's going to start pushing on the big one. And it really looks, when you see it from different angles, it almost looks like they're magnets.
Yeah, but as you can see there,
it really has a real look.
The length of that pendulum on the smaller mass is lower. It's longer. That length of pendulum is going to dictate its period to some degree.
Of them directly interacting, even though obviously they're not directly interacting. So
well, they're not directly interacting, but they are coupled, because it's a coupled pendulum, so they are interacting with each other. because they're coupled. They're basically joined together, and that's not even. So far, we haven't seen the great big lever hanging that's also suspended and swinging, which is a mass that we haven't seen yet. I don't know how big that is, how heavy it is, but obviously it's part of the system, it's part of the whole system. You know, you're just concentrating on these two masses down here when you've got a great big one up there.
And now you're going to start pushing the little one again. So now with each swing, you can see the little one going faster, faster, and then it goes faster.
Okay.
So the energy is being
Calm
switched
down a
over to
bit.
the other side and such. And it goes on and on. And this is a 15
Yeah, it does go on and on because
so
it's
just one piece of energy
gravity.
put in, and this thing went on for 15 minutes.
Potential
Just jump ahead.
to
Obviously it
kinetic.
slows down, but
Potential. Oh, I can't even say the bloody word.
Well, in this case, 4 minutes.
Potential.
There's 7 minutes later. Yes, it's getting a little feeble now, but it's still doing the same thing. And yeah, maybe it runs out in 10. Okay, I walked away, so I didn't watch the whole clip. But anyway, but they're still moving when I got back. That's the point. So obviously, the energy of this experiment does stay in the experiment a long time.
Yeah,
right,
that
so
initial potential you gave it, yeah, is
see what we
conserved.
So this is a better-ish angle, and you know, like I stated, imperfect. I should have made sure this one wasn't moving before I started. So there, I'm initiating the action. All right, so it's pushing on the little one, and with each movement, the little one's getting
because
faster
it's connected
and faster,
to the lever above.
down. And you can see the little one's
So that one's
really
moving the
fast,
lever,
very big arc,
which is then moving over to that one.
Almost stops. It's going up and down, and that's what makes it look like it hasn't stopped, but it actually has stopped. And now the little one's going to push on the big one. So there, I pushed on it, and it pushes on it. And can you see that? Yeah. Yes, you can, even when they're in the way.
But like I say, what we're not seeing here,
it's pretty dramatic when you watch it.
Is you're saying above it's suspended from a lever, which is obviously also swinging. So the whole system, like I say, you've gone from a simple lever to quite a complex. You know, to say this is simple, no.
So now this little one stops. So it stopped, now it gets pushed. Push 1, push 2, push 3, and push 4. So now it's really starting at 5, it's starting to speed up. 6. So the whole idea is instead of transferring the energy in a lever really quickly, you're doing it in little impulses. And obviously you're conserving an awful lot of energy. So the lever is moving up in the air, but it's moving up very little for the amount of action it's
right, creating. You're saying so that, but
there's very little loss.
We haven't seen that so far. You're just saying it's not really swinging, it's just moving very little, but we don't know. And you're saying you've hung it from those distances again. We're not seeing that, are we?
To moving the lever. So the lever is just doing a little movement, and it's creating the very large transfer of the energy from one side to the other side.
No, it's just acting like a bleeding spring.
Pushed again. You can see push, push. It goes faster and faster. The arc gets bigger and bigger.
Yeah, because it's on a longer bob.
In my opinion, this is good enough theory. Okay, now, like I said, we'll see if the buttheads are going to sit there and contest the function of a coupled oscillator and contest that momentum has to be conserved, right. And therefore contest that.
It's not about contesting, it's about what's already known about them. So it's nothing really to contest. It's a coupled pendulum, and that's what they do. They transfer energy.
Experiments basically prove there's no room for two theories. There's only one theory. Either momentum is being transferred between the two objects or kinetic energy is. And the fact is that kinetic energy can't be, because obviously the two objects are different masses, and you can't conserve the momentum and the kinetic energy.
So you say.
Both. I don't know how much more you need to see, and blah, 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 blah. Like I said, see, I can probably run a wire that prevents them from turning, so it'll be even more visually.
Yeah, so they're also turning.
Towards each other.
As well, they're also rotating, which is another energy.
And so that might make it easier not only to do frame rates if you feel it's necessary, or to by some other mechanism. You can always just measure the time of the period, I suppose. But anyway.
Yeah, but I say if you measure the time of the period, you've got to account for the length of the pendulum, which you don't seem to have done there.
So, maybe the lever experiment is unnecessary for the people who recognize that
it
probably has.
Maybe it's unnecessary because you've been actually, now after 2.5 years of actually trying it, you're realising it doesn't work the way you said. So I wouldn't say this is changing the goalpost. This is like moving to a different fucking pitch, really.
Functionally duplicated the exact circumstance and done it in a way where I don't have to waste any energy moving a heavy lever.
Well, you don't have to have a heavy lever, do you? That's the thing, you know. If you say levers do what they do, you don't have to have a heavy one. You could have a really lightweight one that transfers all the momentum.
So the little one stops, big one's moving, and the little one will start moving. The energy will go into its precession. Push, push again. One more push, 2 more pushes maybe, and then the big one will stop. And the little one has got all the energy, and then it'll go right back into the other side again. All right. So
yeah, amazing.
Let's see if we can get physicist Michael to respond to the concept of a coupled oscillator and
a coupled pendulum.
Requirement that you basically have to conserve the momentum.
The angular momentum, yeah.
In doing so, you prove kinetic energy can't be playing a role. All right, probably enough. Yeah, that's the end of the video. All right, so like I said, I'll make the 2 videos available if you want to see them as links and such in the description.